Hey y'all, it's your main math teacher, Mr. Boyden, back at it again. Today we're going to graph rational functions. This is something we've looked at a little bit. We saw this in the previous unit. We called it the reciprocal function, functions like 1 over x. And you may remember that when we sketched those, they made a shape like this. Okay, and so already I've got an example here on the screen. I hope you can see some of the similarities. We've got kind of this sort of horseshoe looking shape, and we have an example right here and right there. In this lesson, they're going to get a little bit more interesting. So there's going to be chunks in the middle. So here, notice we only had our sketch in two different regions. Here it's in 1, 2, 3. It's broken up by vertical asymptotes. So we'll get into that in just a second. Okay, before we can get into actually graphing, we have to know what an asymptote is. Okay, and this is sort of the Mr. Boyden version of the definition of this. For us, it's going to be a line that a function approaches, but it does not actually intersect, usually. Now, the reason it says usually, there are some exceptions. Okay, there's one right here. Here's a spot where the function actually crosses over the asymptote, but typically, the function will get closer and closer and closer to the asymptote but never touch it. Here's another example: closer, closer, never touching, closer, closer, never touching, closer, never touching, keeps getting closer and never touching. So there's a few exceptions, but they're sort of unusual. Before we get into the new meat and potatoes, let's review the old. Okay, we should remember that this little guy right here is graphed like this. Okay, and this is just my best version of the sketch based on my little touchpad here. Okay, and then let's talk about this one. Okay, so what's the 3 doing to the graph, and what's the plus 2 doing to the graph? Okay, well that 3 is a shift upward of 3, and this little guy right here is a shift to the left of 2. So here's the easiest way to do a shift on these. Notice, in this first case, 1 over x, the x-axis was an asymptote. Okay, both parts of this function get closer and closer and closer to the x-axis, but never touch it. Same with the y. Okay, it's getting closer and closer, but never touches it. So what this tells us is that the asymptotes will be shifted up 3. So now I have an asymptote right here, up 3, and shifted to the left 2. Oops. And so then, when I go to sketch my function, it's the exact same thing, but it's just shifted up and left with the asymptotes. Okay, and so there it is. Okay, so if we understand the way these functions behave around their asymptotes, sketching them gets an awful lot easier. All right, so those are the basic cases. For us today, we're going to be graphing ones that are a bit more interesting. In order to do that, we'll need to follow these steps. We'll need to find all the intercepts. We'll need to find the vertical asymptotes, horizontal asymptotes, although that should be singular. There will never be more than one. And we might also find some solution points. So let's talk first about how to find zeros. Keeping in mind that when we say rational, we're talking about functions which have a numerator and denominator. Now when we say zeros, we're asking what would make that whole entire fraction equal to 0. So what would have to be 0, the top or the bottom? Okay, if the bottom was 0, it's not defined, so it couldn't be that. What about if the top was 0? 0 divided by anything is 0? Yeah. So let's fill this in. The zeros, these will always be the values which make the numerator equal 0. Okay, what about vertical asymptotes? These are going to be the ones which make the denominator equal to 0. So if you're taking notes right now, make your notes nice. We're about to do some examples. Okay, and here they are. Let's try to find the zeros and the vertical asymptote of each of these. Okay, so in the first one, the zeros. I don't think that's going to be possible on this one because there's no way to make 1 0. So there are none. And I'm going to shorten VA for vertical asymptote. So that would be whatever values make the denominator 0. So whatever would make x plus 5 equal 0. And I'm pretty sure that would be negative 5. Okay, so that's all there is to it. What about this next one? Let's find the 0. That would be whatever makes 7 minus 8x equal to 0. Okay, if we add 8x to both sides and divide by 8, what we can get is that x is equal to 7 over 8. What about the denominator? Vertical asymptote. It's whatever makes the denominator 0. I believe that number would be 9. All right, let's keep going. What about this next one? For the 0, it's whatever makes the numerator 0. I'm not even going to show the step on this one. We can just look at it and say that that's negative 5. And then what about the denominator? Whatever, so that's, remember, that's vertical asymptotes. It's whatever makes that 0. So maybe you can just look at this right now and see, maybe not. You could add 9 to both sides, so you get x squared equals 9. So x equals plus or minus 3. All right, this is our first case where we have two vertical asymptotes. That shouldn't be shocking. That's the exact same thing we saw in the opening picture today. Okay, so that's the first set of steps we'll do before we can graph. The next thing we're going to do is we're going to find the horizontal asymptotes. Okay, and I do this with something that I call the blowout method. My dear friend Frank, who was my high school teacher, taught me that when I was, I don't know, 17 or so. And it made sense to me then, it makes sense to me now. It's the best explanation I've heard. So here's what we have to know about horizontal asymptotes. Horizontal asymptotes are the ones that really only matter when we're talking about really big or really negatively big values of x. That's when they get really close. The stuff that happens in the middle, it's not really constricted by the horizontal asymptotes. So it's what I'm going to describe it as, it's the behavior of the function when we're looking at really big x values. Okay, so here's what we do. What we do is we keep only the largest exponent of the numerator and denominator. We simplify that, and we think about what would happen if x was really big. Okay, so here's how the first one's going to go. The biggest power up here is x squared, and the biggest power down here is x squared. So I'm going to ignore everything else for a minute. My horizontal asymptote will be the simplified version of this, negative 2x squared over x squared. And you can cancel out the x squared, so that would be negative 2. Let's do another one. In this one, I'm only going to look at the biggest power of the numerator and the biggest power of the denominator. That would be these little guys right here. Let's simplify that out. And what we get is I get 1 over negative x. So, remember, it's as x approaches infinity, or a really, really big number. So think about this. If you take 1 and you divide by a really big number, that actually approaches 0. Think about it like this. If you have $1 and you have 1,000,000 friends, how much money can you give each friend? Well, functionally, you can't give them anything. I mean, it's not technically 0, but there's no denomination of currency you could use. You effectively can give them nothing. Okay, what about this last one? Take the biggest power of numerator and denominator, simplify them, and our horizontal asymptote is x. Okay, that doesn't really seem like a number. These first two are numbers, negative 2, 0, x. This is actually what's called an oblique asymptote, which we're not going to get into too much depth in, but it is something that can happen. So here's the basics, though. That's the blowout method. That's all it is. You're looking at the two biggest things on the numerator and denominator, and when I say biggest things, I do mean the degree, and then we're just simplifying those out, considering what a big number would do. Okay, let's try some graphing now. Okay, here's our first one. The first thing I'd like you to always consider on these is maybe make a list of all the things that we need. So maybe our y-intercept, maybe our zeros, our horizontal asymptote, and our vertical asymptote. It's just kind of laying out a little bit of a game plan. Okay, and so y-intercept, we actually can do that one mental math. So we're going to look over here and we're going to say, hey, that's where x is 0. So if those are zeros, then negative 3/2 is our y-intercept. So negative 3/2. And I like to plot these as I go. You don't have to, but that's what I like to do. Okay, what about the zeros? It would be whatever makes the numerator 0. And remember, the vertical asymptotes are what make the denominator 0. The easiest way to do that on this one is we can factor it. So let's see. We're looking for numbers that add together to be negative 3 and multiply to be negative 3 and add to be 2. So let's try this. X plus 3 and x minus 1. And then down here, let's do the same thing. So we're looking for, looks like x minus 2 and x minus 1. Now, I notice right away, these guys cancel out, which is kind of nice. That's going to make this a lot easier. So my zeros are coming from the numerator. What makes that 0? That would be negative 3. Okay, so I can put negative 3 on my graph right here. Horizontal asymptote, that comes from taking the largest two powers of numerator and denominator, dividing them out. Something divided by itself is always 1. So let's put that in. My horizontal asymptote here is at 1. And what about vertical asymptote? That comes from the denominator. It looks like that's at 2. And that's how I sketch them in, okay? It's sort of a dotted line like that. And so now, I'm going to do my sketching, okay? Now, what we remember is we're going to hit the points that are plotted, and then we're going to get close to the asymptote, okay? So I'm going to come down here, get closer and closer and closer to the asymptote, put an arrow on it, come on through as smooth as I can with this drawing pad, come through the point, get closer and closer to the asymptote. Sometimes it doesn't hurt to sketch a solution point. So for example, I know there can't be any graph up here that would violate the vertical line test, and these are functions. However, it may not be obvious to you right now if the graph is in this upper quadrant or lower. So what we can do is we can pick a value like, oh, I don't know, 3, and we'll plug it into our simplified version and see what happens. That would be 3 plus 3 over 3 minus 2, and that would be 6. So now I have the point 3, 6 on my graph. And now I know that it's up here, it's going to hit this point, and then it's going to get close to the asymptotes. And my sketch is done. That's all it is, y'all. Let's try another. All right, so what do we need? We need our y-intercept, our zeros, our horizontal asymptote, and our vertical asymptote. Now, y'all, there's a lot of similarities between what we're looking at right here and the simplified version on the previous one. So what a good opportunity this would be to pause the video, try this one on your own. Okay, looks like the y-intercept's 1. How am I getting that? I'm doing -1 divided by -1, and that's 1. Let's deal with our zeros. That would come from 3x minus 1 equals 0. Working that out, that would say 3x equals 1, and then x equals 1/3. And I should probably do some graphing while I'm here. So y-intercept at 1, and then I have 1/3 as one of my zeros. Horizontal asymptote. What's that going to be? Okay, looks like I'm going to take these two right here. 3x over x. That cancels, and I get 3. What about my vertical asymptote? What would have made that denominator 0? That would have been 1. So let's put those in. So here's my asymptote at 1. Horizontal asymptote at 3. And again, the left side of the graph looks like it's probably pretty easy to sketch. So I'm going to come up like here. I'm going to then work my way over toward the asymptote. And then what about on the right side? I'm actually going to do a little bit of a shortcut for this one. I'm not going to plug in the numbers. I'm going to show you how to do it mental math style. Imagine I plugged in a number like 5 or 10. Let's do 10. If I plug in a 10, that would say 30 minus 1. It would say 29. And if I plugged in a 10 here, it would say 9. All that I need to know is that number bigger or smaller than 3? It's bigger than 3, and that tells me it's going to be above the asymptote. So all I need to do is I need to be close to the asymptote there, close to it there, and I'm done. Let's do another one. All right, y-intercept. Again, a great chance for you to pause the video and try it on your own. Looks like this one is 3/2, and I'm just pulling the constants off, right? That's very similar to what we did with polynomials, just pulling the constants right off of there. So 3/2 is 1.5. And then it looks like we probably need to find our zeros. So that would be 3 minus 2x equals 0. So 3 equals 2x, and x equals 3 over 2. That's 1.5. Let's find, so 3 over 2. Hey, they're the same. Interesting. Now we need to find our horizontal asymptote. And looks like that would be a minus 2x. Be careful, don't miss the minus over x. Cancel off the x's, and that means we're at -2. So I'm going to plot that in. And then we'll do our vertical asymptote. It looks like we get -2. Again, it's -2 plus 2 would be 0. All right, let's sketch. Okay, this part on the right's pretty easy. Hit the points, hug the asymptote, and then we got to deal with what happens over here. So I think I'm just going to pick a negative number like -3. So 3 minus 2 times -3 over -3 plus 2. And let's see what we get. Looks like that would be 3 plus 6. And it looks like I made a mistake. That's supposed to be -3 over -1. So that would be -9. And what that tells me, and y'all, it doesn't matter that I get the exact right point. The purpose of this is to tell me, is my graph up here or down here? Okay, it looks like it's below the asymptote. So there we go. And my sketch is done. All right, y'all. That's your introduction to rational functions. Hope you enjoyed it, and we'll see you next time.